in today's class, we're going to talk about something called the Executor Framework. And we're going to see how the Executor Framework can be used to decouple the management and creation of threads from other parts of the application in order to give much more flexible and extensible ways of being able to do concurrency. So this is really sort of an advanced threading mechanism in Java. And we'll talk about what it's useful for and how it goes above and beyond, way above and beyond what you get with threads. Although you can do kind of the conventional threading stuff with this framework as well if you configure it properly. OK, so to understand sort of the motivation for this stuff, let's start out by talking about thread pools. So concurrent programs often have to run a lot of computations. If you think back to the discussions we had about the thread gang kind of stuff, we had lots of threads that needed to run to do various kinds of work. You might have a web server that has to be able to handle a large number of clients, and so on and so forth. Unfortunately, the technique that we used with the thread gang, which is basically where we were allocating a thread for every worker that we needed to have done, every piece of work that we had to have done, that doesn't really scale. If you've got 10,000 clients, you probably don't want 10,000 threads. You might, maybe, but if you've got a gigantic supercomputer at your disposal, but probably that would be overkill for a whole bunch of different reasons we'll talk about later. So one way to keep things from getting, so let's ask the question, why do you not want to have as many threads as there are pieces of work to do? What's the inhibitor from trying to do that?
The percentage of your resources dedicated to just maintaining the different threads will eventually exceed the amount of work that you're doing in them.
Right, so there's a bookkeeping issue. You've got gigantic number of threads. They're eating up memory, virtual memory, physical memory. It could make things get excessive. Robbie?
Just running those threads, you don't have that many cores.
You don't have that many cores, right? We're all about virtualization, but there comes some point of diminishing returns.
Creating those threads and context switching is expensive.
Right. So basically, the point here is even though threads are easy to create, you don't necessarily want to have oodles and oodles of them. And we'll see in a second there's some rules of thumb for kind of deciding how many threads you ought to have, and you guys have kind of hinted along some of the criteria. So a much more, sometimes a more effective way is to have a pool of threads. And of course, how big should that pool of threads be? Well, that depends on various factors, right? So it might depend on the number of cores. If you've got 4 cores, probably having 2 million threads is overkill. Probably having 1 thread is underkill, if that's even a word, underkill, right? So you want something that maybe takes into account the amount of physical parallelism on the machine. You may also want to take into account the kind of processing behavior that you're doing. For example, if you have primarily compute-bound jobs, compute-bound tasks, is there a benefit to having more threads than there are core? First of all, what's a compute-bound job or task?
One that's not waiting on external I/O.
Right.
Network.
So it's just sitting there doing some computation, typically doing an algorithm or computing a fast Fourier transform or trying to compute pi to the nth decimal point, whatever, right? So the point is that compute-bound jobs, there's not much point in having a lot more threads than there are cores. Why is that?
Because if you have ones that aren't compute-bound, if they're waiting on a network or waiting on some kind of I/O, that's whenever it becomes useful to sift them out and for them to wait.
Right. So basically, the benefits of threads really come in handy when threads spend a lot of time waiting, and therefore, while one thread is waiting for I/O, for a file transfer to occur, or network, or user to type in something, then something else can be running in the background. But if threads are primarily doing compute-bound things, having lots and lots of them very quickly reaches a point of diminishing returns. So the input, the processing model, the data model, all those kind of things also matter, as well as the number of cores. There are a lot of different ways to organize thread pools. We're going to talk about just a handful of them right now. We'll talk about a few more later. There are many more than what I'm going to cover here. One thing to do is allocate a fixed sized pool. And the idea here is that you create a pool of threads, and those threads will be reused whenever there's work that they need to do. And you queue up additional tasks. If there's more tasks than there are threads to run them at any given point in time, then they get queued up in some kind of queue. And we'll see later there's a bunch of different ways to queue things up. But that's one way to do things. That's a fixed size pool. There's another model called a cached model. And again, there's all kinds of variations of this. What I'm going to describe here is kind of the way that Java works. What they do here is they create new threads on demand. So as new work appears, rather than queuing stuff up, instead it's put in, a thread is created to run it. However, if the threads aren't used by a certain period, like 60 seconds, then they're automatically shut down. So basically the number of threads expands to meet the work to be done, and then contracts when there's less work to be done. Whereas with the fixed size pool, the number of threads stay fixed, and any expansion is done by queuing things up. And we'll talk a bit more about those things a little bit later on. OK, there are a pile of other ways to do this, right? So don't think that those are the only two ways. And there's also variants on that. We'll see later on about things that are called fork join pools or scheduled pools, blah, blah, blah. All right. Here's a nice example of a human known use of thread pools. Anybody know what this is? Yeah, it's back in the bad old days, before we had automatic telephone switching systems. People would sit there. There'd be all bank of operators who would sit there and connect the wires together manually. So that's a good example of a thread pool. There's a pool of people who are sitting there doing stuff, and actually back in those days there probably weren't more telephone calls than there were people to plug them in. But nowadays, obviously, you're not going to have every single person in the country spending time connecting up telephone circuits manually. So there's a pool, and of course, more recently, a call center. When you want to call up and do something with your car insurance or pay off your credit card bill or do just about anything these days, there's a call center and there's a pool of people sitting there, and there are typically a heck of a lot more potential callers than there are people in the pool, and that's why when you call up, it takes for a while to get to the operators because they're in a queue, right? And of course, they typically use the queuing model because your calls are parked in a queue because they don't go out and grab new people off the street to come and answer the phones when the load gets too high. So there's a good human known use, I think. All right, so with that as background, then there's this thing called the Executor Framework. And I guess actually let me change the name of this because it's not the Executor Service Framework. There is an Executor Service, but it's really the Executor Framework. And that's the thing that we're talking about in this context. OK. So this framework consists of a lot of classes. There's a whole pile of stuff in Java that does all this. And the classes are anchored by several interfaces. And you can take a look here for more discussion about it. There's a nice tutorial that exists that explains all this stuff. So kind of at the heart of the whole thing is something that's called an executor. And it has one and only one method called execute, and it executes runnables. We'll talk about that. There is something called an Executor Service that inherits or extends Executor and fills in a whole bunch more stuff. There's something called a Schedule Executor Service that inherits from Executor Service that does a bunch more stuff. And then there's also this other kind of parallel hierarchy that's not unrelated called a Completion Service, which is really cool. And there's an interface called Completion Service, and then there's a bunch of implementations. Maybe I should redraw this slide to take out the Executor Completion Service. That's not really an interface, that's a class. But we'll talk about this later as well. OK, so let's talk about some of these interfaces. Some of this stuff is going to be really simple. Others of this discussion is much more interesting. And you really don't get the true beauty of this stuff until you look at the source code. And we'll do a little bit of that as we go along. So here's an executor. And it's very simple. It basically gives you a way to launch new tasks one at a time. And so an executor has an interface. It's a very simple interface. It has exactly one method, and the method is called execute. And so, and of course, the execute method is going to take a runnable. So you probably know what a runnable is at this point. It's basically something that you can run. It's also known as a task, and we'll talk more about that later. The tasks basically implement the runnable interface, You can find out more about that here. If the executor interface is pretty simple, it's got one method. The runnable interface is even simpler. It's got one method called run. That's all it does. It just does a run. And tasks implement the runnable interface, and they basically implement a command, or they represent a command that can be executed. Now, how have we seen runnables used thus far? What's the way we've seen runnables used up to this point?
They form the guts of the thread. But
Right.
It's actually performing.
So they provide the target for which the thread will be invoked upon. It provides the operation that the thread will do. And we're going to see how this basically takes this idea and generalizes it a little bit. All right, so that's basically what's going on so far. We have this concept called an executor or an executor, and it does the thing. Now, that's also very simple. So it would be useful in many purposes to be able to do a lot more than just say execute. Although, having said that, sometimes execute's all that you need to have done. To do the more stuff, there's something called the Executor Service, which you can look at here. And this basically extends Executor and adds a lot of other methods. And we'll talk about all these methods later, so I'm not going to go into them right now. But the basic long and the short of it is that all these methods manage the life cycle of tasks, and it also manages the executor itself. So for example, you can shut down the executor. You can also go ahead and submit these things and invoke groups of them and so on and so forth. The executive service is used with a bunch of other interfaces, which are very important. And they're actually fairly simple to understand once you get your head around it, but there's a number of them, and they work with each other in subtle ways. And the framework actually goes even further and adds a bunch more that we're going to see later. But here are the basic building blocks. So one of them is runnable. We've already seen that. In the context of this discussion, a runnable is a one-way task that does not return a result. So you give it something. That's why it's a command. You say, here, do this thing. It does its thing. You could also use it to implement various patterns, like command and command processor patterns. You can read about those here. The next method is something that's more interesting. This is called a callable. So if a runnable is a one-way task, then a callable is a two-way task that returns a result. And as you can see by what's happening up here, Callable has a method called call, and call goes ahead and returns a v, which is that's the return type of this. It goes ahead and returns whatever the parameter is. So it returns you the value. And the third thing that relates to all this is called future. And a future represents the results of an asynchronous two-way task. Now, you can also use an adapter to make it work with a runnable and give it a null result. But for now, let's ignore that case for the time being. So a future does a bunch of interesting things. One of the things you can do is you can get the result. So if you take a look here, you can see get and get long. This method, when the computation is finished and the result has been completed or is available, get will return that result. If you call get on a future before it's able to actually have the result done, get will block. You can use this version of get to block for a certain amount of time. You can also check to see whether or not the call is done, and you can also cancel the call and check to see whether it was canceled. So these are some sort of status operations you can do on a future. Futures figure very heavily into some of the more cool asynchronous computation models we can do with the Executor Service framework. You can use this to implement something called the active object pattern, which is a way of being able to invoke methods that run asynchronously on objects. OK, we're going to spend most of our time talking about the Executor Service, with a little bit of executor thrown in. There's some other stuff, though. There's something called a scheduled Executor Service. It extends the Executor Service and supports future or periodic execution of tasks. So you can see here that you can have things that get run back, these runnables get run at some point in the future, either at a fixed rate or with a fixed delay. And so these are things that you can use to run things. They schedule work to get run over time. We're not going to talk anymore about those. The next interface is the completion service. And basically, the completion service decouples the invocation of asynchronous tasks from the consumption of the completed task results. Now, this won't make a whole lot of sense until we talk about the submit method, which is part of the Executor Service framework. And we're going to talk about that, and you'll get to see how that works. Once you understand the submit method and how it returns to you futures and how you can use these futures, then it'll start to make a bit more sense about the Executor Completion Service, which goes one step further and does some really cool things to get the results back very quickly and in a more transparent way. So the key thing you can do here is you can submit callables or runnables, and those things go and run, and then when they're done, you can get the results out of the completion service. This is typically combined with an Executor implementation, although you could implement your own thing that didn't use that. Okay, so those are the basic building blocks. The key thing we're going to talk about here is Executor Service, and then later we'll talk about Executor Completion Service, and we'll show some really cool examples in the context of our string processing example we looked at before when we were talking about various synchronization mechanisms. So then the next question is, how do you make these things? Well, that's one of the more interesting things. If you take a look at the Executor Service, there's really no constructor for it. And the same thing is true for an Executor. There's no constructor. So how the heck do you make one of those things? Well, the answer is you use basically a concrete factory, which is the corollary of an abstract factory, and this thing is called executors. So executors or executors is basically a group of factories. And the various factory methods it defined can be used to create the appropriate executor. And we're going to see a whole pile of examples here shortly, so I'm not going to go into details right now. But one of the things you can do is you can create all kinds of different thread pools. You can make thread pools that use cached models. So you can use thread pools that use fixed models. You can use work-stealing thread pools. You can use single-threaded pools, which is sort of an oxymoron, but you can use them. Scheduled pools, etc. And then you can also define how the threads get created, either by using the default thread factory, which is what this framework uses under the hood to make threads for you, or you can actually provide your own thread factory and get it to use that when it needs to make threads. So the long and the short of it is, when you start using the Executor framework and executors, you don't create threads anymore unless you define a thread factory. Typically, the threads are created for you by the framework, and they're managed for you by the framework. And that gives you a lot more flexibility. So that's that whole thing about decoupling stuff. Okay, here's a little discussion about what a thread factory is. It's just the factory method pattern. There's a bunch of common Executor implementations, and we're going to see a bunch of these in action. I'm going to give you a quick overview right now, and then we'll talk more about them later. One of them, probably the most common one, is called the thread pool executor, which you can read about here. And basically what it does is you give it a task, which is handed off to this thing, and by the execute method and so on. And it goes ahead and runs the work in a background thread. And it has this thing called a worker thread, which you can see down here. Whoops, you have a worker thread down here. And there can actually be a group of worker threads. There can be one or more worker threads that are spawned in a variety of ways, which we'll look at later. And you can also define the type of queue. If you look carefully here, you can see this thing called a blocking queue. And there's a bunch of different kinds of queues you can have. So one kind of queue you can have is called a direct handoff model. And that uses something called a synchronized or a synchronous queue. And this is a really funky queue. The only purpose of this queue is to directly hand off the work to be done to a thread to do it. That's its only purpose in life. You can't put anything in it. It doesn't even have a size of 1. You can just use it for what are called rendezvous operations. The nice thing is that what you do when you do this is you basically end up spawning a thread for every piece of work to be done, which gives you some benefits in terms of dependencies and avoiding deadlock. The downside is you end up spawning a lot of threads if you use this model, because you're not really queuing anything up in your pool, in your queue. You're just basically creating new threads. Another model is called unbound queues. The nice thing about unbound queues, an example of an unbound queue would be something like a linked list or an array list, something that will grow to get bigger. And the nice thing is about bounded or unbounded queues is that if you have lots of bursty requests every once in a while, but otherwise you don't have a lot of work, you can smooth out the processing when you have a lot of work to do. And then when there isn't much work, the resources are basically reclaimed and you don't waste resources. The downside is you can allocate lots and lots and lots of work, runnables basically, and stick them in the queues. So it can grow without bound because it's an unbound queue. And then the third kind of thing would be a bounded queue, which is just a queue that you've put a bound on. It's some kind of queue that you said, I don't want any more than this capacity to be there. By the way, every queue is ultimately bound because it's the maximum size of the memory. Eventually you'll run out of memory. But usually when you talk about a bound queue, it's like the number 10, not 800 gazillion, right? The bounded queues limit resources. They're harder to tune to figure out what the right size of the queue ought to be. And you can end up with deadlock if you're not careful. OK, so that's one kind of pool. This is by far the most common pool. And we'll see a bunch of examples of how it's used shortly. There's another pool that's kind of interesting called the fork join pool. And this is used with Java's fork join framework, which is part of the Executor framework. And basically, it allows you to take problems or algorithms that can be recursively decomposed into smaller parts. So the classic example of this are MapReduce style problems, where you want to search a large space for something or some things. And you do that by breaking it up into pieces. And then you run each part of the problem recursively. Quicksort would be an example of a fork join style problem, although you probably wouldn't use concurrency to implement it. But you can break things. It's basically for divide and conquer algorithms. And what you end up doing, essentially, is you end up creating a tree of threads with queues that they're processing and doing work on. And one of the cool things about a fork join pool is that if you have threads that have been created that are doing work and they run out of work to do, they will go around and try to steal work off of other queues in the framework. And the idea there is their goal is to never block if there's anything to be done. So it's kind of like, people who are obsessive compulsive and when their roommates aren't there, if they don't have anything to do, they'll start cleaning out the dishes and doing people's laundry and stuff like that, right? They just got to stay busy, right? So that's basically the idea. So the idle threads try to steal work from queues that are busy doing something so that there's a maximal utilization of the number of threads that can do something useful. So that's a fork join pool. We're not going to talk much more about that, but it's pretty cool. There's a nice discussion of it here. And then there's this third thing, which is we're going to talk about. And this really isn't an executor implementation, but it's used in conjunction with an executor implementation. It's the execution completion service. And it uses an executor to execute tasks, and it takes the tasks that are finished. You submit them for processing. And when they're done, it sticks their futures into this blocking queue. And then another thread of control can sit there pulling the results and processing them as they finish. So it's a really cool way to be able to have this sort of pool of threads off doing some processing and then one or more threads handling the results. And you can do some really neat things with that kind of a model. OK, so that's basically the key thing. So let's kind of dive down a little deeper into each part of this stuff. We'll start by talking about the Executors class. And this basically defines these factory methods and some other utility methods that are used by all the other stuff in the Executors framework. For example, one of the things that the Executors class defines is a thread factory that is used by default to put threads into a known state. And so when you call execute or submit, and there's a need to have threads that are going to go ahead and be running, and there's a variety of ways this works. They may get pre-spawned at startup time. They may get spawned on demand if you have cached thread pools and so on. Whenever a thread needs to be created, the Executor framework goes and uses the thread factory that's been configured to basically go ahead and make a new thread. So there's a method called new thread on the default thread factory, and this goes ahead and calls that, and it gives you back, it gives the framework back a new thread. Now again, how that's used is internal to the framework, but the point is you don't actually spawn these threads. They're spawned on your behalf. If you want to control something about the threads, then you'll have to come along and subclass from thread factory and then provide your own factory method to make a thread. And you'll see, as we see a little bit later on, you can pass thread factory objects into the various factory methods of the Executor. Here are a bunch of methods that make fixed size thread pools. So check this out. This is pretty cool. So there's a couple of methods. You'll see that most of these methods have two forms. One that just has the number of something, another that has the number of something and a thread factory to make the threads. So that's typically the way they work. So here are two things. Notice that in both these things, the implementation of a fixed thread pool is to create the same number of core and max pool size threads. You'll see for the other models, like the cached model, the core pool size is 0 and the max size is unlimited. For a fixed size thread, the core size and the max size are the same. It's whatever you want the thread pool size to be. So that basically means that they're going to be allocated at startup time. Moreover, it means that these threads will not time out. They'll just keep running in perpetuity till you shut everything down. The threads can block on a shared unbounded queue, and by default it's a linked blocking queue, but there are various ways to customize this in a whole bunch of different means, but by default you get a linked blocking queue, which makes sense. That allocates memory one chunk at a time as you need it. And of course the threads can be created by a default or custom thread factory. So you can either take the default one or you can customize it here and pass it in there. So that's a fixed size thread pool. You'll get a little chance to play around with those fixed size thread pools in one of the upcoming assignments. Here's the next thing, a variable sized thread pool. So in the variable sized thread pool, called new cached thread pool, things are a little different. So once again, you can use the factories, but new threads are started as needed, but existing threads are reused when available. So here's what this says. This says the core size is 0, which means no threads spawn by default. And it says we are going to be able to spawn threads up to the maximum integer on the machine, which is a big number, where you can spawn like 2 billion threads. Of course, your machine will melt down long before that happens, but in theory, it's unbounded. However, if work comes in and there's already a thread that's been created and that thread is not currently busy, then it'll be reused to hand the work to. If threads are not used for 60 seconds, they're recycled. Now, execute, when you call execute, it actually does a rendezvous using this weird thing called a synchronous queue. That's a synchronous queue. And as I mentioned before, a synchronous queue has this interesting property that it will block until something is taken from it. So a offer call, a put call, or what's called offer, will block until someone comes along and does a pull or a take. And of course, threads can be created by the thread factory. There's also some other methods. These fall into the category of utility methods. And one of the ones we're going to see later that's kind of cool is something that's called Callable. And Callable is an adapter function that is passed a runnable task, and it goes ahead and creates a new runnable adapter. And this is kind of cool. Check how this works. So the runnable adapter takes a runnable. What is a runnable? What's the characteristic of a runnable? It has a run method, and it doesn't return a value, right? It doesn't return anything, so it's a one-way call. So this allows you to take a runnable and create a runnable adapter that converts runnables into things that you can use that will be used in the context of a callable, right? So check out, the runnable adapter takes a runnable and returns something that can be used as a callable. And of course, the way it does it in this case is we just make its return value null. So it just turns into nothing, right? It just returns a null. But you can still use it in a context where the syntax expects to have a two-way call. Okay, so that's basically executors. There's a few more methods in there, but those are the key ones, and certainly the ones we're going to use. All right, let's talk now about the Executor Service class, or Executor Service Interface. So it's basically an interface that extends Executor, and it provides some additional stuff. So here are the classes out of the box that actually implement Executor Service. So we have Executor Service, and then we have Abstract Executor Service, and then we have Thread Pool Executor, Fork Join Pool, and Scheduled Thread Pool Executor. These are the key classes that are going to be inheriting ultimately and implementing Executor Service. And you can find all the source code here. It's really cool to poke around in this stuff. It's really fascinating what they're doing. All right, so let's talk about some of the key methods for Executor Service. Now keep in mind, these methods are implemented by these classes, right? So this is just an interface. So I'm going to tell you what they do, but not how they're implemented. We'll look later at how they implement. So here's a couple things. First of all, there's methods to submit tasks to be run. And of course, the execute method comes by inheriting from Executor. It's not actually in Executor Service, but I just put it here so we wouldn't forget about it. And this guy basically does one-way operations that don't return any values. Then there is the submit method. The submit method is more interesting. It passes in a so-called callable, which has a method called call, and call returns a result. And what it returns is something called a future. As we saw before, a future is basically a way of accessing the results of computations that run asynchronously when they are done. Right? So it's like a promise to do something at some point down the road. So the way this will work, of course, is you'll call the get method of the return future. You or someone will call the get method at some point in order to retrieve the value. And we'll see some examples of this shortly. There are also some really cool methods that allow you to do group operations. So there are methods called invoke all, a couple of different methods called invoke all. And this allows you to go ahead and run all the methods in a collection. A collection would be like a list or something like that. Runs the methods of all the items in this collection. And it then returns a list of futures. So think about this. You're starting a bunch of things in motion, and you get back a list of futures for things that are still out computing. And then somehow, we'll see how later, you go and you resolve or you get those futures. You redeem those futures to get the results. Obviously, you should not modify the collection while invoke all is running. That would be a bad thing, right? There's also another method called pair of methods called invoke any. And invoke any are even more bizarre in some sense. They go out and they take a collection and they go and find the first result that came back successfully. And they return that result. So it doesn't return it as a future, it just returns that result. Any other results that have not, any other tasks that have not started to run are canceled. And any other tasks that completed have their values ignored. Can anybody think of what you might want to do with something like invoke any? Why would you ever want to use it?
If they're all the same, all the tests you're calling?
Right, but what would be an example of why you do that, Lawrence?
Let's say you want to compare merge sort and insertion sort, so you start them at the same time. Whoever gets back first wins.
Yep. Yeah, that's the canonical thing. You've got some group of either algorithms, or maybe you've taken the data and you've partitioned it in such a way where you want to go ask many things to run in parallel, and whoever comes back to you first, you just take the result. You don't wait around for anybody else to come back. So that's basically the idea with invoke any. That's potentially, obviously, wasteful, but hey, what the heck? We got lots of cores these days, so if it can go faster, go for it.
So does it wait for someone to complete before it returns?
Well, so in this case, this will just block until somebody comes back. In this case, this guy will wait up to a certain amount of time for something to come back. Jake?
But the invoke all, so the futures, they don't block until you get from the future. Is that right?
Right. With futures, it doesn't block until you try to redeem them. At which point, if it's done, you got it. If it isn't done, then you block. But there's operations to do timed operations. You can also check before you block. You can say, are you done? That kind of stuff. A lot of stuff that Google does, when you go do a Google search, it basically is doing an invoke any, but on a huge cluster of processors, not on a couple of threads on one machine. It's doing large scale speculative computation, taking some result and then giving that back to you. There's also a bunch of operations for shutting things down. One operation called shutdown does an orderly shutdown, which basically completes existing tasks, lets them finish, but ignores any new ones. So once you call shutdown, at that point anybody else who comes along will be ignored. And then there's also something called shutdown now, which basically goes out and tries to cancel existing stuff or interrupt it. And it certainly doesn't process any waiting tasks that haven't run yet. This gives you back a list of what was waiting. So if you shut down now, you'll get back the list of things that didn't run. And then there's also a bunch of methods to check the status of shutdown. So is shutdown checks to see if the executor has been shut down. In other words, somebody said shut yourself down. Is terminated checks to see if everybody's finished running, all the tasks have completed after the shutdown. And await termination is used to block up to some timeout, waiting for everybody to shut down. So what you might do is you might say shutdown, and then you do an await termination. And then when await termination returns, then you know that everybody's shut down. Why do we need all this stuff? What the heck is the problem that's trying to be solved here? Why can't we just call shutdown and be done? What's the fundamental underlying issue that makes it necessary to do this kind of thing?
And if it turns out they hadn't shut down yet, and then you're trying to access something they're working on, then that's a problem.
So part of the problem is just knowing when the threads have reached a quiescent state, I guess is the best way.
When it's safe to access what they were.
And also when it's safe to leave, right? This is a little bit like the discussion we had the other day about, when you close your store down, somebody's still in the restroom or whatever, you don't want to just turn off the lights, set the alarm, and leave. It'd probably be bad. So you want to kind of say, flip the lights, say, hey, 15 minutes, the gym is closing down, everybody finish your workout and leave by 10 o'clock or whatever. And so that's kind of like shutdown, and then await termination is kind of waiting for everybody to leave. And obviously, there may be, you may not be able to wait forever, so you may wait for a certain amount of time, and if they haven't shown up, then it's like, okay, I'm leaving the process now, goodbye. I'm gonna dynamite the store, right, if you're not out of here by this point. A little bit draconian, but it gets people's attention.
The store is blowing up.
Yes.
5 minutes.
It's like one of those James Bond movies, right, where they're going to launch the warhead or something like that, And of course, they always have this long countdown, giving James Bond a chance to show up and save the day. Jake.
So all of those are kind of like what you call shutdown. That's kind of requesting all of the threads to shut down. So what would you do to kill them?
Who is you in this case?
If you're the executor, or if you have the executor.
Yeah. So the main thing you would do is you would do the interrupted stuff, the thread interrupted stuff under the hood. That's the safest and cleanest way to do it. But again, remember that's somewhat advisory, right? So if everything is always voluntary when it comes to shutting stuff down. If things are really ornery, then you probably are just going to say wait termination. I'm going to wait for a minute, and if you don't, get out of here, kaboom, right? I'm closing the store. There's probably I don't know. Bruce Willis or Sylvester Stallone movie that I could come up with here that's along those lines, or Arnold Schwarzenegger. All right, so that's Executor Service, and as you can see, we'll see how it works in a second. I'll give you some examples, but that's basically how it works. You can use it to either execute tasks that are runnables and one-shot things. You can use it to submit two-way things, and the way it gets information back to you out of the box is to give you back either a future per submit or a list of futures if you do an invoke all. So those are the two ways that things work. Now, there's a couple of things to think about, and to motivate this stuff, let's just think about what happens. When you get back a future, how do you know when to redeem it? Right? That's kind of a tricky issue. If you don't have anything else to do, you can just call, get, and it'll block. If you have something else to do, you might call get with a timeout, or, is done or whatever, and you could check, and you could kind of check periodically, and if it's not done, you can go and do something else and come back and check. But that all seems kind of haphazard, for lack of a better term, right? Now, when we have a list of futures, things get even more complicated. Can anybody think about why that would be complicated? So if you have a list of futures, how are you going to find out what's finished, and what would be tricky about that?
Well, you can't block on all of them at the same time. So you have to block. If you were going to block, you have to block on one, and then switch to the other, or block with a timeout, and then switch to the next one and block with a timeout. So it's very slow to iterate the whole list.
Right, and inevitably, the one that you start out with will return at the end, and all the other ones will have finished long before then, right? So sort of no matter what order you look at these futures in, the naive way of just having a loop that loops through the collection of futures saying get, undoubtedly they're all going to do it in such an order that it takes the longest amount of time to get done, right? Because you spend all your time blocking on the one who took forever, and by the time he or she finally finishes, everybody else has long since been done, but you couldn't actually deal with those. Okay, so given that as the context, waiting for things to finish, right? Let's talk about the Executor Completion Service. So what this does is it basically combines itself with an executor, and what it'll then do is when you submit something, as we'll see, this basically kind of overrides a few extra things here. Let's see if I can find this. So this is what the thing looks like, and here's the source code. So what it does is it basically gives you some similar interfaces to the Executor service. You have submit, a couple flavors of submit. But what these things do is rather than giving you back the information, they set stuff up so that when the calls complete, in other words, when they're run asynchronously, rather than giving you back futures, instead they stick the stuff into a blocking queue in the order that they complete. And here's the blocking queue. They put this thing called a queuing future, which we'll look at in a second. They put a queuing future into the blocking queue, and then you can call take or poll, and we'll talk about the differences there later, and that will then run in a separate thread of control, pulling out the results as they occur. So you can have, a pool of threads running a bunch of results, and another thread waiting for the results to come back. And the second those results are done, that thread's got them out and has processed them, which is typically going to be a lot more responsive than the way of starting up a bunch of requests, getting back a list of futures, and then doing what we were just talking about with Nathan, blocking or polling each of them individually over and over and over again. So that way, which is more of a synchronous way of redeeming a future, is being replaced with the Executor Completion Service with an asynchronous way of getting the things redeemed. And it's based on callbacks. And you would typically run this in a separate thread, although you don't have to. All right, so let's take a look. This is some really cool stuff. The source code is quite fascinating, and it shows you a lot about concurrent asynchronous processing in Java. And these are just patterns. This is just classic pattern stuff, design pattern stuff. So we have some methods for submitting either callables or runnables. Let's focus on callables. Runnables are just the same thing with an adapter. So what you do here is you submit a value returning task, whatever that may be. And that is defined as a callable. Now look carefully at this. So this guy has a method called call that returns a value called v. So callable has a call. This is where the logic goes. You get back a result. Call is synchronous. The context in which call is called is typically in a separate thread, in a pool of threads, that's asynchronous from the original invoker. So that's an important and subtle distinction we'll see later. Okay, now if you take a look, you can see that there's a method here inside submit called new task for that takes this callable, and new task for takes the callable and it returns something called a future task. But just to make it wacko, it returns it as something called a runnable future. So what the heck is a future task and what the heck is a runnable future? Well, let's first look at future task. Oops. And I think I have, I'll go back and look. I think T should be capitalized in future task. So future task basically does the following. It goes ahead and stashes away the information that's passed to it in its constructor. So over here, it puts the task that was given it. And then what the future task does is in its run method. Now remember, its run method is going to be called in another thread of control. It's part of the pool. When the future task's run method is called, it goes ahead and makes a two-way call, gets the result of the call, stores it here, and then it takes this result and it calls a hook method called done. Remember the done method. It's important. That's what future task is adding. Future task is giving a way for its run method to invoke the task it was passed as a callable, storing the result, and then it's going to call the done method. And there's a way in done you can get access to the result. All right. But here's what future task implements. It implements runnable future. Here's runnable future. A runnable future is both a runnable and a future. So a couple weeks ago, Lawrence had said, can you have interfaces that inherit from other interfaces? Well, here's a good example of where they go berserko with this, right? So runnable future extends both runnable and future, both of which are interfaces. So runnable future is a runnable future, which means it has the run method and all the future methods as well. And it defines the run method. And that's the guy, this method, runnable future, is going to be passed into something called a queuing future. This is getting very complicated, isn't it? So what a queuing future does is the queuing future basically is a future task, and the future task keeps track of the task, and when his run method finally gets called, which is over here, he's going to go ahead and get the result, and it's going to store it in such a way that over here, when the done hook method gets called, which is called there, that turns around and adds the completed task with its return value into the completion queue. So we finally reached the point now where this completed task is in the completion queue. And then, of course, we'll see in a second, to get the results back, you call one of these methods, take, poll, etc. And that goes ahead and pulls the next completed future. See, it's a future. It pulls the next completed future off of the completion queue. Now, there's a couple different ways to do this. One way is to call take. As you may recall from our earlier discussions, take will block until there's something in the queue. If the queue is empty, it'll block, so it'll wait. Poll returns either null or whatever was in the front of the queue. So it doesn't block, it polls. And then poll with a timeout will wait up to a certain amount of time for the future to show up. You can use different models for different purposes. If you have a separate thread of control that is running, reaping the results of the asynchronous computation, you would probably have it use take. If you're reusing the same thread of control to execute or submit tasks and also to check for their completion, then you'd probably use poll, either blocking or either non-blocking or timed poll. Let me just make sure everybody's clear on what's going on here. Do you see that basic model? So you're sitting there with a thread of control, like sending stuff out, and then you're able to get the results through a queue that's managed for you by the Executor Completion Service. All right, so lots of cool stuff. What I've done over the last couple days is I went back and I re-implemented my TaskGang framework, came up with a way better way to do it, which is committed into GitHub if you want to see it. And now it's called the TaskGang Framework. And it's way cooler. And so we're going to use this to illustrate all the things we're talking about. So here's the TaskGang. Some things are still similar. We still have this gang, and he has some of the same methods as before. And then there's a bunch of other things that are used to provide various kinds of implementations. So let's quickly go through this. This is sort of a recap of what we saw before, but it's been generalized. Now remember, with the ThreadGang, there was a thread for every source of input. But that was problematic because we ended up with perhaps too many threads. So now we're going to use a TaskGang, and we're going to parameterize where the unit of computation comes from. So it might be a regular thread, or more likely it's going to be something from the Executor Framework that's used as a thread pool. All right, so what is a task? Well, as we said before, a task is a runnable command that can execute in a background thread. That's just the way that task is used in Java. It's not really a data structure, it's just a concept that's implemented with a method called run. Okay, so here is basically the idea of the TaskGang framework. So we're going to have a bunch of input sources, input cycle 1, input cycle 2, input cycle n. And those input sources are then going to be mapped to some number of threads that are going to process them. And the cool thing, what we're going to see now, is we're going to be able to decouple the number of input elements that have to be processed per cycle from the number of threads that will process them. Before, they had to be one and the same. There was a one-to-one mapping between input data and thread to process it. Now we're going to be able to make that much more flexible, which gives you a lot more leeway to do different kinds of things. All right. So here's the common part of the framework. These are the common methods that everybody implements or is available for people to implement. The italicized stuff are things that are abstract, and you have to define. The non-italicized stuff are things that have default implementations. There's a bunch of common algorithms and control flow that come built in. The run method basically gets the next input of whatever size it happens to be, and it initiates a TaskGang, and it gives the input size, but you're free to do whatever you want. That you can allocate a thread per input element. You can allocate a thread pool. It's whatever you want to do. That's a hook that you can fill in. And then await tasks done is a method that is used to wait for all the things to be finished, which might take multiple cycles or not. This is a template method in the good old template method fashion. You can customize this in several ways. You can override these methods through subclassing and then change what it means to do an initiate TaskGang or await done. Or you could also just override run altogether and change its behavior, either way. Here's the make task factory method. This is used to make a task. Here's the default behavior that it does. It makes a runnable, which is a task, as you know, and its run method gets the input that corresponds to the index that's passed into make task, and it processes that input, and then it goes ahead and if it succeeds, if it fails, it returns. Otherwise, it goes ahead and says task done, which is a hook that can be used to customize what goes on next. And once again, you can modify this in various ways. All right, here's where things start to get interesting. And when we look at the code, you'll see how this gets used very, very cool ways. So one thing you can do is you can customize where the data comes from. And it's as long as it comes to you as a list, it could actually be coming from a file. It could be coming from a network connection. It could be coming from strings. The framework doesn't care. You can also control how many cycles to run. And that's controlled both by whether there's any more input to be done, as well as whether or not you want to advance to the next cycle. Those are used in slightly different ways. They could probably be merged, honestly. And you can do this to either do cyclic or one-shot type of processing. The other thing here that's very different from what I had before, but very cool, is how to structure the threading and synchronization. So we're going to have a method to set and get the executor service. So you can decide what kind of executor service you want to have. Do you want to have one that's a fixed size thread pool? Do you want to have one that's a cached thread pool? It's up to you to make that call. You can also decide how, so that's one thing, what type of executor, fixed versus cached. What type of concurrency model? Do you want to have a thread pool? Do you want to have a thread per input element? By the way, I should point out that you can use the Executor Framework to have a thread for every element to be processed. And the trick there is to define the appropriate execute method for the framework, which you can customize trivially. And you can use that to go ahead and spawn a thread every time you call execute. So you don't have to have a pool if you don't want to. And then the final thing is what kind of synchronizer, which could be any of the things we looked at before in the previous lessons. Now, here's a little bit of trivia for you. So cyclic barrier and countdown latch sometimes require you to know in advance how many things there are to wait on. Phasers don't require that. You can have phasers used for a dynamic number of things, as we saw before. But cyclic barriers really need to have threads, a separate thread for everything that's trying to run. So you can't easily use a cyclic barrier with a thread pool-like model, because once you run out of threads in the thread pool, then there's no way to get to the point where the barrier can be released, because those other threads will be blocked on the cyclic barrier, and the pool will be full. Now, if you have a cached pool, of course, then you could allocate more threads. So you have to be a little bit subtle. It's a little subtle. What processing to perform on each element? And one of the really, really cool things we're going to see with the new version here is that we're going to be able to get massive amounts of concurrency and asynchrony in the new framework. So you can make things concurrent based on input sources. You can have a thread or a pool of threads for each input source. And then, which we didn't have the ability to do before, but now we can do, we're going to be able to do for every thing we want to do to the source of input, we can make that run concurrently as well. And I'll show you how to use some of the cool advanced asynchrony features in Java in a second to how to do that. OK, and you can make a decision. Do I want synchronous versus asynchronous processing of the work? So this allows you to get really highly concurrent processing in very cool, flexible ways. And then how do you wait for the tasks to complete? Do you wait for thread join, countdown latch? Do you wait for shutdown on the executor service? Lots of different ways to do that. OK, what we're going to do now is we're going to go ahead and finish off the examples of using the executor framework. So I went back and reworked all this stuff, so it's way cooler. And I hopefully can show most of it just by using the slides without having to go into the editor and go around. We'll see if that works or not. So what we're first going to do is we're going to talk about the TaskGang Test. So this is the TaskGang Test. As you can see from this UML diagram, the TaskGang Test is basically it's basically a test driver that has a whole bunch of nested classes inside of it. And all of these nested classes inherit from search TaskGang common, and search TaskGang common in turn inherits from TaskGang. So we've talked about the TaskGang framework before. We're not going to talk about that again. We're going to re-talk about TaskGang common because I have a better way to explain some of it. And then we're going to walk through each of these different subclasses of TaskGang common. And I'll show you the cool thing that each of them does. Yes?
I know someone had mentioned this on the discussion forum, and they said that they had searched for TaskGang and didn't see anything. Is this something that you came up with?
Oh, yeah.
Okay.
It's my creation. I need to find, I want to find an icon that's a cigarette. I'm going to take the Java guy and put a cigarette in his mouth, or have a bunch of them, like maybe wearing leather jackets, or so there'll be a TaskGang. That's kind of the image I want to have, like hanging around street corners, yelling at people concurrently. So you can get all the latest code has been committed in here. I keep changing it, compulsively as I play around with it more. I'm pretty happy with the way it is right now. It shows a lot of cool stuff. So this is basically what it does. So the TaskGang test customizes the TaskGang framework to search for words in a list of strings. And so there's a bunch of different sources of input. So if you were to look at the class, you'd see there's a bunch of strings defined here. These are our sources of input. Now the cool thing is you could change all this stuff as you saw fit. If you don't want to read from strings, changing this to work from files is trivial. So I just used the strings because it was easy for me to look at the output and know what the heck was going on. But you don't have to be limited to strings. That's just to make it easy. So we have what are called one-shot input strings. This is for the one-shot tests. We have fixed input strings. These are for the fixed tests that cycle multiple times. So this is separate cycles. Each cycle has the same number of strings. And then we have a variable number of input strings, where we have cycles, each of which has a different number of strings in each cycle. So that's just there to be a cool test driver. Of course, you could add more to it. There's also an array of the search words that we're going to look up in the input strings. So here's the word list and just musical notes, and these are strings that contain musical notes. So that's just a string of this stuff. And actually, I cannot believe I did that. It's funny, I went back and very carefully changed M word list. I forgot to update my slide. So, all right. So that's the input. And this is important, and you'll see this later why this is important, because the kind of concurrency we're going to use is either going to be a function of the number of inputs to search or the number of words to search in the inputs, or both. Right? So you're going to see when we get to the final approach I show here, it's just concurrency out the wazoo. Everything's concurrent. Right? Now there's 4 tests to run, and this was kind of fun. I keep learning new cool things about Java, which I probably should have known, but never had a chance to have an excuse to learn. So with Java, you can have a set of enumerators. So this is a numerator with enumerated literals, one for every one of the tests. And then you can define basically an iterator that loops through all these things. And I'll show you that a little bit later. So it's real cool and real clean. So here's the first thing we're going to do. This is the executor one-shot test. And you'll see for each of the tests that we're going to look at, there's a little bit different thing that they're doing. So for executor one-shot, we have sort of 3 main things that vary. There's a few other things that vary too, but they're not as important. We have the executor model, fixed size thread pool, variable size thread pool. Those are things that can vary. We have the unit of concurrency, which in this case is a task per input string, where each task can run concurrently. So what that means is that each input string is being processed concurrently. And then we have the results processing model. And this approach, as we'll see, uses a blocking queue to store results for immediate concurrent processing. That means as soon as results are done, as soon as results are processed in one thread in a task or in an executor, they're put on a queue, and then the processing can start on doing something with it. So here's kind of what things look like under the hood. So we've got the input strings to search, which in this case, the color red here just means these are the things that are actually going to run concurrently. So some number of these things will run concurrently, which is a factor of the number of threads that are in this fixed size thread pool. So this is a thread pool executor. It's got a fixed set of worker threads, let's say 4, just for sake of argument, which means up to 4 inputs can be running at the same time. We then have the search words. Here's the search words. We'll color those red when time comes. Here is the results queue. This is a blocking queue. It's a linked blocking queue, but it doesn't really matter what kind of queue it is as long as it's a blocking queue. And it contains these things called search results. Search results contain where the words were found in the input strings. So it just keeps track of where they were found. And the way this is going to work is when we say execute, when we execute a task, the runnable that corresponds to this thing will be put into this work queue inside the thread pool executor. And then one of the threads in the queue, when it's available, when it doesn't have anything else to do, will pull something off the queue, take it off the queue, and then run it. That's kind of the workflow that you're going to see. So that's the executor one-shot. All right. Here's executor cyclic. So executor cyclic also has fixed size thread pool, except it's going to have a cycle of things to process. So we're going to have, one set of input words followed by another set of input words. And we could have as many as we wanted. We're just going to do 2 just to keep it simple. But you could have n, where n is big. And by the way, it's going to turn out we could also vary these things if we wanted to, just because of the way that tasks work. The unit of concurrency here is a little different. It's kind of cool. We're going to put everything into a collection, and then we're going to call invoke all on that collection. And that'll go ahead and run everything in one fell swoop. So it's going to take everything in that collection and go ahead and run those things. And it's going to put the results into a future, a list of, or not, take it back. It's just going to go ahead and run them all. It's not going to put them anywhere. It's going to run them all. And it's also going to use a blocking queue that's going to restore the things for immediate processing. All right, so that's the cyclic version. Not dissimilar from the one-shot version, except we use invoke all this time instead of doing them one at a time. The next one we do is a one-shot version that's going to change a bunch of things. First of all, it's going to use a variable size thread pool. So it's going to use a cached thread pool. Does anybody remember the difference between a fixed size thread pool and a cached thread pool? Jake?
Cache pool, the active threads can, if they don't have anything to do, they'll take something else off the queue. Or if they don't have anything to do for a while, they'll just die.
Right. There's one more thing you're right.
It'll spawn more as needed.
As there is the queue, there is no queue, basically. There's no, that's why I have like a worker queue with only one item in it. So when you execute something, it goes and does a rendezvous, and it waits until a thread has been either created or there's one available to pull the thing off the synchronous queue and then process it. So it'll spawn new threads on demand.
Could you have a cache with like a limit, like with a cap?
Right. Yes, you can definitely do that. Absolutely.
Is
Yep.
that common, or?
It could be, yeah, if you don't want to let the threads grow that bound. Wait, I take it back. I'm wrong about that. Cached, the underlying mechanism allows you to do that, but I think that maybe I'm wrong about that. Let's look that up. That's worth knowing. I can't remember that. Let's say Java Executors. Nope. It looks to me as though it'll just create new threads as needed. So there is no cap. Now you could write your own variant of this thing that would do that. But if you start putting a cap, then you probably need a queue.
Right.
And the reason for that is it's very easy to get into deadlock if you're not careful. And you probably didn't see what I just saw, but you just have to take my word on it. Okay. So this will use a variable size queue. It has 2 other important differences from what we saw before. The main one is that rather than having the input strings be the unit of concurrency, instead The search words are the units of concurrency. So for each search word, we're going to run a lookup of that search word concurrently on the input string. So it's kind of flipping things around. It's changing the concurrency focus. And we'll talk about that when we get to that example. We'll talk why would you do one versus the other. And then the other thing we're going to do is we're going to use the synchronous future model for deferred concurrent processing. So what's going to happen here is you're going to go ahead and submit a bunch of tasks corresponding to the number of words that you have to search. And then each of those things is going to return a future. You're going to create a list of those futures. And when you're all done with that list, you're then going to go in another thread and you're going to say, while that list is not done, get the results one at a time. So that's a deferred processing because you have to wait till all the things are kicked off, so you have all the futures, before you go wait for anything to do. And we'll take a look and see how that works. So that's the third model. And then the fourth model, which is really my favorite by far, is the Executor Completion one-shot solution. That uses a variable size thread pool, a cache thread pool. It decides to go completely off the deep end. So it makes both the input strings and the search words concurrent. So everything is running as a task. And wait till you see, it's really cool. And it uses asynchronous futures for immediate concurrent processing. And that uses the Executor Completion Service, which allows you to kick a bunch of things off and then wait for them to complete. And as soon as they're done, you get the results. So you don't have to do deferred processing. So I was having fun. I was reading this stuff up. I was looking at the code. And I was like, wow, the Executor Completion Service really looks like the ProActor pattern, which is a pattern I actually wrote about in one of the books on pattern-oriented software architecture. So I sent an email to Doug Lee, who wrote Executor Completion Service, and I said, Doug, is this really the ProActor pattern? He's like, yes, that is a ProActor pattern. So I was very happy about that. But then he said, but that's considered somewhat passé. And what's really cool now is something called completable futures. And I was like, oh, crap, now I got to learn something else. So I decided to look at completable futures. I have to show this to you. I will actually get out of PowerPoint to show this to you. So, completable future. This is a Java 8 hot off the press thing. Let's see. So basically, here is the remember the interface for future has like get, right? It's like got two methods: is done, get. Okay. Here's the interface for completable future. I decided I would not cover that in today's lecture. So it does an awful lot of cool stuff, I'm sure, because Doug is a great guy and he's a guru of pattern-oriented concurrent processing. But I thought maybe we'd wait to figure that one out for a little bit later. So it's obviously very, very complicated. OK, so let's take a look at the rest of the TaskGang Test, not TaskGang Test. So we define a factory method to create the tests. So you guys are familiar with the factory method pattern. This guy gets called, and he goes off and creates the appropriate tests based on the parameter that's passed in. And then here we have the main function that iterates through all the tests to create and run them. So the tests to run values, if you have an enumerated type, which we have, which is called tests to run, if you go back over here, you will see tests to run. It has a bunch of enumerated literals. If you want to iterate through this thing, you simply say tests to run dot values, use a for each loop, and then you just take the result that comes back and you can use it as a variable. So we're passing in the enumerated literal one at a time into the make TaskGang factory method. So that's kind of cool. You may already have known that. I didn't know that until I looked at this and I was like, wow, that's pretty cool. All right, so that's the test driver. And I showed you that mostly to give you a big picture view of all the different kinds of ways we're going to mix and match these different Executor Framework models. So here's the Search TaskGang common class. You can see this inherits from TaskGang, and it's basically the base interface for everything else either directly or indirectly. All right. So here is what's search TaskGang common. So you have a bunch of input strings you're going to search, and you can do them in cycles. So that's the words to find. We use an iterator to be able to systematically access these things one at a time. It makes the code really concise. Here's what the code looks like. If there's anything in the iterator, we go ahead and increment the next cycle, and then we go ahead and get the next item in the iterator. So that's real clean, real simple. Each task runs exactly the same logic. So you create a new search results data structure, and then there's a loop here that goes and looks for the word in the input results. And every time it finds it, it creates a search result element, and it adds it to this search results thing. And when it's done, it returns that. So that's how it gets the work. Notice this is embarrassingly parallel. So there's really no dependencies between each of these things. They're all completely independent of each other. Here's what a search result looks like. So a search result, basically under the hood, it uses a linked list. And it keeps track of the thread ID, where the thing was found, the word that was looked up, the input data, and what cycle it was. In other words, where I was the first cycle, the second cycle, third cycle, and so on. And then it also goes ahead and keeps track of the index into the string, the input result, and which you could have for any given string. You could have multiple indices that match, because the word might appear multiple times. Here's the barrier that shuts down the executor and waits for everything to exit. So this is a good example of using the shutdown and await termination methods on an executor in order to wait for it to finish all of its processing. And notice that there's no commitments yet to all the really cool things that are fun, right? So the things that are fun here are stuff like the executor implementation, whether it be cached or fixed, the type of concurrency model, how many threads we have, whether we're doing things synchronously or asynchronously with respect to input processing or result processing, where are we getting the input strings from. All that stuff is left as an exercise for implementations later on, which are then added by all the subclasses. So these subclasses come along and fill in the blanks. All right, so let's talk about the first example here. We'll kind of dive down a little bit and look at some of the code. So this is search TaskGang Executor one-shot, which is kind of a mouthful, but it basically is a search TaskGang subclass that does things once, and it uses an executor. So here, just to remind you what it's got, this has a fixed size thread pool, task for each element in the input string, and a blocking queue that stores the results for immediate processing. So let's take a look. It uses a fixed size thread pool. Here's an example of how this thing is made. We go ahead and first create a countdown latch with the number of input elements, and that's going to be used to control when we're done. And then we go ahead and we make a new fixed thread pool with max threads, where max threads is set equal to 4, let's say. It also contains a blocking queue. So you can see there's a blocking queue. And this blocking queue under the hood is implemented using a linked list. It could be used an array list as well, but we use a linked list for link blocking queue. And there's a method called processQueuedResults that goes ahead and creates a thread that's going to wait in the background and process all the results that are put into the results queue concurrently. And we start that thread, it runs in the background, and when it finishes, when it processes all the requests, that thread will exit, and then we join it. So this is a good example of thread barrier synchronization, a very simple example. The init TaskGang method goes ahead and creates tasks in the executor thread pool. And what it's going to do, now keep in mind what's going on here. Let's go back over to this picture here. It's going to go through every input string that we're going to process. There are 8 of them, let's say, just for sake of argument. And for each of those things, it's going to go ahead and call execute. And the parameter passed to execute is make task. Now, we looked at make task when we looked at the TaskGang Framework. And what make task basically does is it returns a task, it returns a runnable, whose run hook method calls the process input hook of this class. So we're going to create basically 8 of these runnables, each of whose run method will call process input. Process input, in this particular case, iterates through every word in the words we're looking for, and it searches for the word in the input data. And that's going to return back a search results data structure that keeps track of the number of times that word appeared in that input. And we're going to go ahead and call QResults. So for every word, we're going to look up in the input to see how many times it appears. That will build a search results object, and that guy gets given to QResults. And then QResults adds the search results to the end of the blocking queue, and then process queued results, which has got a thread running in the background, will sit there and loop, taking each element out of the queue and printing it. So we have the classic sort of producer-consumer situation. We've got a pool of threads, processing, looking for the words or whatever you want it to be doing. As those threads, as the runnables, the tasks complete, they put the search results into this queue, and then a separate thread of control sits there pulling stuff out of the queue and processing them.
So these threads actually aren't returning data, they're just actually accessing like the shared queue.
Yeah, all the threads are doing, that's right, they're not returning anything. All they're doing is process input, it just returns a Boolean that says did it work or not, which is ignored in this case. But process input is simply calling this method, and this method is doing this processing, and for every word, it's coming up with a list of search results for that input, and it's sticking that in the queue. So that's a pretty, so going back and looking at the picture over here, it's probably easier to see. So we've got these threads running here. They're running tasks. Those tasks are processing, one piece of input each. As the input is being processed, for each of the words that's being looked up, the results are being stuck in this queue. And then there's a separate thread over here that's processing the queue. That's a very common model. It's actually a very, very cool model because you can have a lot of asynchronous tasks running, and as they complete, they're sticking things into a common queue that then is processed by one or more threads to pull stuff out. You could actually have multiple threads pulling stuff out if you wanted to. Now, just a little bit of side note. I didn't do this because I didn't want to get too carried away, but if I was really writing something like this where performance was really important, what might be the problem with the model that looks like this? We've got these various worker threads processing the input. Here's input. We've got these worker threads processing the input, and all of these guys are then throwing their results into this bounded queue, and we have, let's say we have one or more threads. There could be more than one. We have one thread at least pulling stuff out of the queue and doing stuff with it. What do you see as the potential bottleneck in that approach?
Well, the one thread may not be able to process all the results fast enough so that the queue could get filled.
So this queue might start to grow, right? That's one problem. Yeah.
There's no rules saying you have to have an equal number of threads pulling and taking. So unless that happens, which is unlikely, you're always going to have a situation where either the taker or the putter is having problems.
Well, yes and no. So let's assume that this queue can grow and shrink as need be. So as long as the queue doesn't fill up, we're probably OK. So the issue there is the point that Colin was making before. If this guy takes longer to process stuff than these guys take to generate stuff, eventually this queue is going to fill up, right? And then something will happen. It may not be a problem, but that would be a problem. I'm looking for some other problem, though. Jake?
If you prioritize generators over producers over consumers, could you have starvation issues?
You could. So there's definitely starvation issues possible here, but I'm looking for something else.
Is it because the access to the queue is synchronized?
It's the access to the queue is synchronized. Why is that a problem?
Because if one, it's kind of like what you were saying with starvation issues, but it could be that one thread is continuously putting, which is blocking all the other ones from putting in. So you're going to have waiting issues.
But we could. Let's assume for sake of argument, we don't really care what order they show up in, as long as they get processed eventually. So if the goal here is to just get as much work done as possible, what's the deficiency? You could actually sort of see it visually here.
Well, you're not going to be running concurrently at that point if everyone's trying to access the queue, and that's like what's holding them up.
Exactly. So there's a lock here, right? And in fact, if you look at the queuing implementation, it's going to use condition object and a reentrant lock, blah, 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 right? So this becomes a contention point or a constipation point, if you will. So what we would probably prefer to do, and the reason why this is a problem is every time we get done with the search result, we're putting stuff in the queue. So this shared lock is being hammered, and the more threads we have running here, the more this guy's going to get hammered, right? So what we might want to do, which would be a real easy fix, would be to have these threads not put results in this shared queue right away, but instead have their own thread local queues. So they could have thread local queues, and thread local queues would be queues that would not require locking in order to be accessed, because they'd only be accessed by one thread. Right? So this guy would just go ahead and stick things in his thread local queue. And then at some point, like at the end of a phase or whatever, at an end of a cycle, or whenever the queue got full, you could pick the model. At that point, then you would take these items, and then you would go ahead and give them to some queues to process. So the idea there would be you'd have a lot less constipation on a single choke point, because you'd be growing things locally, and then at the end of that, you would then merge them together. So that way you wouldn't have as much contention per run. You would have some contention, but it would be at the end. Any questions about that? And you can imagine all kinds of things in everyday life that work like this, right? You can imagine all kinds of situations where you're working someplace and you're doing something. When you're all done, you need to take your results and put them someplace else. And if every time you're done with one piece of something, you have to walk over and put it somewhere, you'll spend all your time going back and forth, right? So what you'd probably do is you'd probably build up a big queue of things, and then when, at the end of the day, like an inbox or an outbox or whatever, at the end of the day, you'd walk it over and say, here's all the work I've done today. So that's basically the idea. Okay, so this model is very similar to the one before. Let's see. So the blocking queue holds the results, prints the things out, and then here's the await tasks done method. This is the main barrier synchronizer. And what it does is it goes into a loop, and it processes all the queued results up to that point. It then waits for all the threads to exit, and of course the threads exit when the task is done. And then it checks to see if there's anything else to do. By default, await advanced task to next cycle returns false, so everything is a one-shot task by default. So this thing will only run one time. And then it goes and calls up to its superclass's await tasks done method, which is the one that goes ahead and shuts down the executor and then waits for all the threads to stop in the pool. So that's basically, this is what the main thread spends its time doing. It's basically processes results, waits for the cycle to be done, checks to see if there's any more cycles, and when there is not, it then shuts everything down. And this is barrier countdown is just used to count down by one. All right, so that's the first one. Let's take a look at the second one. This is the cyclic executor cyclic. The only differences here are that we have multiple phases or cycles of input to process, and we're also going to do this cool invoke all thing, which is really fun. Now, when you look at the implementation, you can see that we're getting most of the implementation from the one-shot class. So we're not having to do a whole lot of work. We only have two methods we're overriding. This, of course, is the beauty of a framework. It's like a contest to push responsibility, push implementation up the inheritance hierarchy, so more things below can reuse it. This is the cool part. Initiate TaskGang. What this guy is, remember what Initiate TaskGang did before? Let's go back and look at what Initiate TaskGang did before. What Initiate TaskGang did before was for every element that was in the input, every input element, we called make task, and we executed it. So that would go in a loop. What we're going to do over here instead is we're going to start out and we're going to create ourselves a worker collection that's going to be an array list. So it's an array list. And then we go through, and for each of the input sources, we call make task, and we turn what make task creates, which is a runnable. Remember, it has a run method that calls process input. We turn this into a callable by using the runnable adapter that the executor's factory method class supports. And then we add that to the worker collection. So when we're all done with this, we have a list of runnables, which are being masquerading as callables. We need them to be callables. And then we say, hey, ExecutorService, invoke all of these callables in this collection. And that'll go out, and in one fell swoop, we'll start them all up. So once we have the collection, we can then say invoke all, and that'll go ahead and run them all. So now they're all running concurrently, doing their thing, right? So that's basically how that works. So that's kind of cool. And then, since this is cyclic, when the main thread is, when we have to check if we're going to keep going, we see if there's any more input. And if there's no more input, then we go ahead and we return false, except I have a syntax error there. Let's see. That looks a little better. So what we do is we go ahead and get the next input. If it fails, of course, we're done. If we have more input, we go ahead and call initiate TaskGang again. And the cool thing about this is that it gets reinitiated for each cycle, so the whole thing starts over. And you could make the size grow as you saw fit, because there's no need to be fixed. All right, that's the second version. The main thing that did to the first one was it uses invoke all, to invoke all the elements in a collection. The third example, now we're starting to get to some really interesting stuff. This example uses a variable size thread pool, and it uses a task per search word. So we're no longer using a task per input string. We're using a task for each search word. So each input string is then concurrently searched by different tasks, each of which is looking for a different word. And we're going to use the synchronous future model that'll defer the results processing. All right, so first let's go ahead and use a cached thread pool, which is created like this. Really piece of cake. Say executor's new cached thread pool. Here's what process input does. Okay, this is pretty cool. Let's see. Yeah, so let's take a look at this. So process input. Remember process input. When process input gets called, and we'll see how it gets called in just a second. But when it gets called, it's going to go ahead and it's going to iterate through all the words it's looking for. And for each word in the list, and as you saw before, there's some number of words, let's say 8 words, it's going to submit a new callable to do the processing. And the callable it submits is going to, of course, run in a background thread. Remember, that's what we're doing. We're submitting callables. They're going to run in a background thread created by the pool, or created by the cache thread pool. And the call method is going to search for the word in the input data, and it's going to return a search result. Now, if you recall, submit actually returns a future. So it calls the call method, which synchronously returns a search result, but that thing gets bundled up into a future, and that future gets passed back as the return value from submit. So we create a future called result future. And then we have this other thing called a mResult futures, which is a list of futures of search results. And so it adds each future to this list of futures. So we're kicking off a bunch of tasks which will run for every word in one input string. And all those things can run in parallel in the pool. And as many words as we have running parallel, there'll be threads being spawned to run them. So the results are stored in the futures list, and then they're added to this list. Here is what initiate TaskGang looks like. So initiate TaskGang, unlike what we saw before, doesn't spawn a separate thread or a separate task for each source of input. Instead, what it does is it creates this mResults futures array with the right number of elements in it. And then it goes ahead and calls, for every input string, it calls process input on that string, which of course then turns around and does this thing to make all the words run concurrently. And then the last thing it does is it starts processing the results after all the asynchronous calls have been invoked, have been submitted. So this is a slightly different results processing model. With the other models, as soon as we started running the work, we could be processing results. In this model, this call will not run until we've kicked off all the asynchronous lookups. And there could be a lot of them, right? There could be a lot of asynchronous lookups going on here. Yeah?
The adding the feature to the list, that's atomic, right?
Yes. Yeah. Yep. Well,
Right.
this is in one thread of control. So whether this was atomic or not, there's only one thread of control that's doing this.
So the in results features is specific to that thread?
There's only one thread that's accessed. There's only one thread that's updating this data object at a time. This thing is also done in the main thread. So this is where it's allocated. This is where it's accessed, but that's in the main thread. Good question. So this is a slightly different thing. This is kind of the so once we've done that, once we've got all the list of futures, then the process future results method gets called, which you saw it got called here, and that turns around and it iterates through all of the futures and calls get on them. Now, here's the kicker, right? Get is going to block if the results that it corresponds to haven't finished processing yet. So the synchronous future processing model that we just looked at has limitations. The limitations are you can't really start to redeem the futures until you've created them, right? So you have to kind of wait till all the calls are kicked off. You can't sort of do them at the same time. And that doesn't take that long to kick them off because they're asynchronously started, but still, it's not a zero amount of time. So you can't start to process the results. And secondly, if for some reason you try to block on a get call that isn't done yet, you block. Now, of course, you can do a timed, you can do a non-blocking check, but eventually it just becomes awkward to do things like this. All right. So to overcome the problems with the synchronous future processing model, we're going to have one more approach, and this is the Search TaskGang Executor Completion one-shot class. And what it's basically going to do is it's going to overcome the limitations with synchronous processing by using the Executor Completion Service, which is way cooler and allows things to go in parallel or run concurrently. Once again, we're going to have a variable size thread pool, but now both the input tasks and the input strings are all going to run as separate tasks. So assuming you have gobs and gobs of cores at your disposal, boy, you're going to have a lot of fun. Now, honestly, some of this stuff is just to show you how to do it, right? In practice, everything here is all compute bound, because we're not really doing I/O. So it's probably overkill to spawn, a gazillion threads. I'm just showing that you can do it, right? I'm not saying you should do it, just saying how you could do it. So the mechanism is being demonstrated, but the policy is a little bit contrived. However, if the input was coming from network connections or files, then this would make a lot more sense, because it would make sense to have multiple threads. So every input is going to be in a task, and every search word is going to be in a task. So let's see how the heck that's going to work. We're going to use the cached thread pool, just like we did before. The difference is we call new cached thread pool, and then we go ahead and call Executor Completion Service, and we connect the Executor Completion Service with the executor that we created up here. So we create an executor, we create the right kind of executor, and then we go ahead and stick it into the Executor Completion Service. And what will happen here as the tasks are completed by the Executor Service and its threads in the thread pool, they're going to stick it into an internal queue, which is called a completion queue. And the internal queue will then make that available to the main thread, which will sit here blocking in take, waiting for work to do. So that's going to allow us to be able to concurrently process the results as soon as the futures are done. So this is actually not unlike our original approaches where we built our own queue, where we had our own blocking queue. But now we use the one that comes built in to the Executor Completion Service. So each data element is processed concurrently. So you can see here we're going to go through and create a task for every data element. And as soon as that's done, we're going to say start processing any results. Whenever those things show up, we're ready to go. You'll see what that does in a second. And then for each of the tasks that we call for each data element, we're then going to go ahead and submit yet more work. We're going to call submit here. So this is going to go ahead and have every word looked up concurrently. So basically everything is running concurrently at this point. Notice how we are ignoring the futures returned by this submit call because they are going to be handled instead by the executor completion service. All right, here's where the things get done. This is concurrently process queued futures. This guy just sits in a loop, and he sits in a loop taking stuff off one at a time and calling print on it. And take will block as long as there's nothing there. Get will not block because it something doesn't show up, a future doesn't show up in the queue until it's finished. That doesn't even happen, right? That's because it uses this thing under the hood called a future task. So this is going to not return until the future is ready, so we call get. We're always going to be able to run it. And so that way, this thread over here will just keep running, running, running. These guys are generating work. This guy over here is consuming work. Now again, we're making wild assumptions. The input strings we're giving are very short, so it won't take long to search them. In reality, you would probably have something looking in a giant database, right? So it would take a long time to do a search. So probably you're going to be doing long times for searching and then a relatively short time to process the results. So this current model makes a lot of sense. If that didn't make sense, you might want to have a pool of threads back here working off of this queue. That would be another model. So there's all kinds of different ways to break this up. OK, so any questions about that? So that's basically what the code does. And you're welcome to take a look at it. There's obviously more subtlety and nuance than what I showed you with these little slides. But I think the slides hopefully get it across at a fairly high-level way without getting mired down in too much syntax and stuff like that. OK. So any other questions about any of the topics we covered here? Yes, sir, Lawrence.
So if you had to define a future in, say, one line on a quiz, what would be a good definition for what a future is?
Why
you would use one?
So a future is basically an object that gives you access, it gives you deferred access to the results of a computation that runs asynchronously or concurrently. And it separates out the invocation and processing of some computation from getting its result back. And of course, you would use it because you want to allow those things to run independently of each other without requiring a thread for all the things. It's basically a way to be able to allow asynchronous communication that doesn't require a blocking thread for everything you're doing.